Well, sorry for this little intro here. I thought there was going to be a little recording on first, but apparently it isn't, so I'm just going to start with a formal. So welcome to today's webcast, brought to you by Lightwave. Today's event, Emergency Restoration Fundamentals, will be presented by myself, Larry Johnson, Director and Founder of the Light Brigade. A couple questions you may have before we begin. These are housekeeping items. You can expand the slide area by clicking on the maximize icon in the top right of the slide area, or by dragging the bottom right corner to enlarge. In fact, you can expand and reposition any of the components on your screen, so feel free to arrange as you desire for your optimal webcast viewing experience. At the bottom of your audience console, there are multiple application widgets you can use. If you have any questions during the webcast, you can click on the Q&A widget and submit your question. We will try to answer those questions during the live Q&A portion at the end of the webcast. If you experience any technical difficulty during the webcast, please click on the Help widget. It has a question mark icon and addresses common technical issues. If you still need assistance, just type your issue into the Q&A widget, and a member of our webcast support team who's monitoring the program will work with you to correct the problem. Any additional resources for this webcast can be downloaded via the resource list widget that looks like a green folder at the bottom of your screen. For your convenience, this presentation will be available on demand within 24 hours of this live event. A reminder email message will be sent to all registrants with a link to the archive, and it will also be accessible through the Lightwave homepage. And so now we will start the formal session. As I mentioned before, my name is Larry Johnson, Director and Founder of the Light Brigade. I believe the next slide we already covered through the housekeeping issues, so we'll move right into a little background on the Light Brigade. And that we were established in 1986, industry leader. We teach and develop courses internationally. It's always fun to work with individuals and organizations to develop curriculum specifics to themselves, or to have them attend any of our open courses. The last bullet on this page is we're also upgrading our emergency restoration course as we talk, so this is always fun. And we always welcome questions, examples. If anybody wants to send us photographs or have experiences that they'd like to share, it really is interesting. And of course, we want to not only teach the normal things that we run across in communications, but also some of the abnormal experiences. And I'm going to bring up a few while we talk today. So the basic philosophy, though, is 3 words: identify, locate, and resolve. So if we have a problem, we want to identify what the problem is. We'd like to locate it as soon as possible, and the resolution takes the longest part. So we're going to work on these. But we can also talk about the types of failures and where they occur. So we broke these down into different elements. So the system-related, so in other words, these are transmission system, powering type issues. When we start getting to the optics themselves, a lot of times it's at the patch panels and cross connects, primarily because this is where people have access to the fibers and that. So good, proper fiber and cable management is very important to minimize these types of outages. And then, of course, we get to the larger outages, which tend to be caused by construction-type activities, human error, sometimes vandalism, and probably the worst case, Mother Nature, such as typhoons, tornadoes, landslides, earthquakes, and these tend to be catastrophic and very extensive. If for any reason that you are in an area of the world where certain types of events occur, such as, say, Guam, where typhoons are major, then you develop your plan based on the worst thing that could happen. and that it can always be easier, but you want to deal with the past, and that's why we say history repeats itself. It really doesn't matter if a communication cable goes down, whether it's coax or twisted pair or fiber optics, and that a tree falling on a cable doesn't care what the media is within the media itself. I also want to just point out this picture. It's one I took years ago, and I was asked to attend a construction site at the request of a carrier, and what it was is they were installing a new water main, and as many of you may know, a certain carrier in North America likes to concrete encase their fiber optic cable. Well, when I got on site, one of the first things I saw was this guy walking on that concrete encasement, which is non-steel reinforced. Well, the issue is to prevent the outage, not react to it. So as soon as I saw this, I go, you got to get this guy off. But I just happened to have a camera, and I took a quick picture. But the fiber cable is literally on what he's walking on. And that. So when we look at types of outages, and that, we try to look at them from causes and effects. So in one case, while we can see that cable cuts account for 25% of all major outages, and the largest cause of those is human error, which accounts for 40% of that 25%, and that the average outage takes over 5 hours to repair. And so we're going to talk about each of these different items there. And the different typical types of fiber damage, again, I love taking photos and having them sent to me. So in this case, a bullet penetration into a cable. But you can have a complete cut where the cable is completely cut in half, or partial damage, which would occur in a case like this. You can also have high fiber attenuation, and we want to stress this point that just because you found where the break point is, or the specific damage point, that damage can extend before and after that element, and we want to use our skills and our equipment to know exactly how far damage extends from the actual break or damage point. And open fibers where they break, these are pretty rare nowadays, and for those that have been in the industry for decades, really, it was mostly caused by the types of coatings and cable structures which were still new for the industry, but they do happen occasionally, and a lot more on the older cables that were installed versus the new one. Some other types of problems occur are aerial and ducted, and whether it's a gunshot, lightning, trees and branches, fires, vehicular. I saw one case where aerial restoration, someone was trimming the branches around the fiber optic cable, and they actually cut the cable during the trimming. So people have to be very careful when it's around. It's not always obvious, so it's nice to have somebody on site or making sure people understand the nature of the construction itself. In ducted or direct buried circumstances, we have dig-ups, whether they're caused by augers or backhoes, and that rodents will eat anything in front of them, so we try to protect them, and you may have different types of rodents in different parts of the world, so take a look at what the best preventive answers would be for that specific critter. Icing, which puts stress onto the optical cable, but most of the time our real problem is when we have a splice closure that's not sealed properly, and we get water intrusion, and then it freezes and it stresses the fiber, and it may not break the fibers, but it's going to stress them to the point where your system can go into alarm. And that, of course, collapsed or crushed ducts and improper installation. Okay. Other ones, underground, say you're trenching and that you backfill with not the best soil, and so we're putting maybe the cable in on top of rocks or lava or other things, and then we're putting top soil on it, and it's stressing the cable itself. Things that aren't planned, but washouts, where all of a sudden a landslide or so takes out a hillside, and very rare can an optical cable withstand that type of load effects. But so in this case, you're going to have damage much further back than just the case where the break itself may show up on an OTDR. Want to also point out the picture on the upper right with the auger. If you notice, the cable's coiled around the auger, but so is the warning tape, and we actually buried cable in different scenarios and then dug it up to find out what the cause was and what the problems were. And one thing that was very obvious real quick with augers was the warning tape coiled up on the inside first, and then the cable would coil up. However, it was also noted that in most cases optical fibers survived this, but they were stressed by it. And that one of our studies also found that when we had augers, that sometimes people would have the cable and that they'd take it off, put it back in the hole, and in one case they put the telephone or the pole back on top of it, thinking nobody would notice or it was an abandoned cable. It was pretty obvious when you went out on site to look at it. The other photo down at the bottom right is an example of just buffer tubes entering into a splice tray into a splice closure. It's pretty obvious that we have a bent or kinked buffer tube there. The technician should have seen this right up front, but you want to look for these. You want to dress your closures properly. You want to do your sealing of the cable ports, but also the closure in this case, and then a flash test to make sure that it's properly sealed to prevent moisture intrusion into it as well. So we want to really talk about planning, and we want to talk about how to develop a plan and that for it. So to do so, we have to cover lots of different items. So we have an email address here that you can email to, and we can send a questionnaire over to you if you're interested. We always suggest that you customize the restoration plan to your application, and you may end up with multiple ones because you may have aerial, underground ducted, underground direct buried, just different scenarios. I always recommend people take the worst case and build the plan around it, because this way life can only get easier. And then address both retrievable and non-retrievable slack scenarios. Retrievable slack would be such as a ducted installation where slack cables kept in multiple vaults along the route, or in aerial spans where, again, you have slack cable at multiple locations. Whereas a direct buried would be a non-retrievable installation method, and therefore if the cable's cut, we're going to have to cut back and install a segment of cable and bypass the original cable. So there's different elements that need to be addressed, including the equipment, and that could vary from heavy equipment, backhoes, and different trucks and so forth, or bucket trucks, for example, or it could be OTDRs, power meters, visible lasers, etc. We're also affected by the environment. A majority of restorations take place in bad weather, and that weather is a vehicular damage or tree-related damage or Mother Nature type, but the environment plays a big part in it, and it affects the resolution of the restoration itself. You also have different members in the staff, and we'll talk about some different roles that people play in different organizations. Again, the size of your organization also has a big impact on this as well. Smaller organizations, people wear multiple hats, and you may outsource a lot more for contractors. And last but not least is making sure you have the right tools as well. Okay, so part of this pre-emergency planning is to assemble an emergency response team, and so this could incorporate different people in different departments: construction, installation, repair, engineering, transmission. Determine, whether you have standby cable and hardware on site or easily accessible. Remember that a restoration may take place at midnight on a weekend or so your local distributor may not be accessible to pick up materials. So you really want to make sure that you have the right hardware and cable for quick access. We also want to make sure that your system maps and drawings, sometimes they're called as-builts, are current and accurate. You want to know where all your splices are anyway, and during the initial installation, you should have your links set and as well as attenuation values using the OTDR. You want to also work with the transmission equipment to know what your loss budgets are and what the dynamic range is, or the variance that you can have on the repair. So if you're running a real tight loss budget, then it makes it a lot tougher on a temporary repair. And we'll talk about temporary versus permanent more slides up. But you do want to know if you have a 5 dB range and that or safety margin. That it gives you a lot more flexibility, especially if you want to do a real quick emergency repair. And then that gives you time to come back in better weather with the right materials, with the right crew, and do a permanent repair and then get your new post materials. Call list is not only for your internal staff, but it could be for key contractors that you're going to use, whether it's for construction, again, bucket trucks, backhoes, or the case of staff that you have. And of course, some people don't have their cell phones on when they're at the movies. So you may want to have a couple, instead of just one person, 2 or 3 people. So if you can't get one, you go to the next person. But we can't wait for a movie to be over to get a restoration started. As far as documentation issues, again, we're starting on the plan. You want to develop a restoration plan based on what types of outages potentially you could have. Once a restoration's been, or once your installation's been completed, you want to compile the final as-built report, but also remember that after the restoration, we're going to update that report as well. And acquire the cable data manual. Put this together. Remember that whatever cable you purchase may not have the same fiber in it from vendor A, B, and C. So matching the optics. So that cable data manual is very important because we want to know whose fiber is in that cable, and we want to know specifically whose fiber it is, and which type of fiber. So many manufacturers have a half dozen or more types of it, say a G.652 standard single mode fiber, so you want to know which one it is as well. Also, determine the routing plan for the cable, and in case of a failure, prioritize circuits so that if you have, say, 911 circuits on it, that may be the first fibers to repair, and they're probably not going to be the blue and orange fibers in the blue buffer tube. Also have your attenuation report, again from your as-built, your final OTDR measurements, your final optical loss measurements, your values for splices, splitters, connections, whatever. And if you are going to put together an emergency restoration kit, make sure that you have a good bill of materials list for that as well. And keep an eye on expiration dates on those. So you can see the importance of the documentation, and we start this during the initial acceptance testing of the span. We actually start it when we start procuring the cable, for example, so that we know whose fiber's in it and so forth. The performance, we want to know the optical loss. Depending on the complexity of your network, you may add dispersion calculations into it, and of course we're really critical now on the reflectance of connections and the optical return loss of the span itself. And again, keep the documentation current, and which means that anytime you're doing maintenance that you're using it as a comparison, but you're also updating it when any changes have been made. And we want to do this to address the restoration requirements. Now, one case of this that's very important is the fact that your cable comes in with either sequential meters or footage. Hopefully not both. If you're going to be in footage, be in footage. If you're going to be in metric, be in metric. But don't switch back and forth. It makes it much more difficult. And it's really something right now with long lead times on optical fibers and cables. There's a tendency to shortcut to get a cable, and you can acquire it, purchase it, but it's in footage, and you've been working in metric. Not a good idea, and that you'll pay for it in the long term, and I'll talk about a few examples later on in the session. But the sequential markings give us a great assistance in the installation and maintenance and restorations. But you need to document both the incoming and outgoing markings wherever there's storage or at splice locations. And these are going to be useful for reconciling actual cable distance with geographical distance and locations. So in this case, we just showed 2 vaults, and we showed the sequential markings coming into the vaults, or you could say coming into the splice closure, and they even be more technical, how much is inside the splice trays themselves. But the cable length should still be documented on the as-builts, and then if you can note the slack fiber, that much better yet. Okay. So one of the things that we work with fiber optics is what's called the index of refraction, and this is actually the propagation speed of light in an optical fiber. Now, I gave you 2 numbers here, what the speed of light is in miles per second in a vacuum, and then in a typical fiber, single-mode fiber, what the speed of light actually is. And if we divide this in, we'll get an index of refraction of 1.471. Now, if your supplier has an index of refraction of 1.468 divided in, and you'll get the actual speed at the different setting. However, remember that the OTDR measures fiber length. It does not measure cable length. And so we're depending on the technician to compensate by this additional fiber length by using the sequential cable markings to acquire the correct cable length. To do so, the best time to actually get the index of refraction that matches cable length is when the cable reels first come into your yard. In this case, you have the markings at each end of the cable. That tells you the exact amount of length in meters or footage. And now you adjust your index of refraction on the OTDR so that it matches that same sheath length. That number, that new index of refraction number, which I call the cable index refraction number, can be used in your as-built drawing. So if something is broken or damaged into the future, you're not worried about being off 5% on accuracy on a span. Now you can get them down as close as we can optically for it. Okay. To continue this, we need to know, the technician would need to know the fiber size. In this case, I'm using single mode as the greatest example. The type, so this could be a G.652 standard single mode fiber, or say a G.655 non-zero dispersion shifted fiber, as well as the manufacturer. And the reason for the manufacturers, different manufacturers use different techniques to make the preforms that the fiber is drawn from. This will also affect when you're splicing the splice quality. While it may be a G.652 fiber, and they may have to, whether all the fibers would have to meet the optical and mechanical specification as defined in the ITU's G.652 standard. The manufacturing technique's different, and when you splice different manufacturers together, you have to compensate with the fusion splicer on a different prescription so it matches the size. The second thing, the size and the type. The second thing is the tolerances change from one end of the fiber to the other. We have a program, a 1-hour online program called Light Bites, which really goes into detail on single-mode tolerances, single-mode fibers, and different techniques. And it's something you can take at your own time. You can look at our website and find out more information on that, or just email us and we can give you that information. So remember, the manufacturer's index of refraction values for the fiber and does not match cable length. And the last bullet, measure from the last known physical location. What we're saying here is if a fiber's broken, and you take your cursor on your OTDR and you set it at a break point, then what you want to do is use the 2-point technique, an A and B marker, put the B at the break, move the A back to the last known splice point, and measure the difference there. Quick sip of water there. Sometimes when you're talking a lot, your throat gets dry. Okay, so restoration equipment, here's our typical equipment: the optical time domain reflectometer, the optical power meter, visual tracers, inspection scope, and cleaning kits, and then we're requiring good documentation. Each of these is valuable in its own case, and we'll talk about each of these separately in the importance. Something else I want to talk about is what's called an emergency restoration kit, sometimes called a jump kit. And they should be designed based on your requirements, the products you use, and the techniques required. The length of the optical cable, you're better to use the excess cable that you have from the construction to build your own restoration kit. This way it matches the cable structure, it matches the fiber type, manufacturer, etc. You can build it with your own splice closures on, and again, the situation here is if you're in a ducted environment, this isn't going to do you any good because you can't pull the closure through the duct, so you may end up with only a one-ended restoration kit, or each of the different pieces, but they're all kept together. And of course, making sure that whatever splice technique you're going to use, mechanical or fusion, that you have the right equipment and the right tools to do so. Maybe it's the best idea just to build your own, and this way you can also use it as a practice as well. So if we have a restoration, the initial response is verifying that it is a system outage, and then we start going through a series of lists on who we contact in what sequence. So the first part, again, is identify that you have a problem, and then we start going to the location on that. But the first part here is identifying, yes, we have a problem. Different departments start getting involved. The restoration crew now has to know where the fault is, and we're going to depend on the speed of the field activities to actually find the location. The OTDR will get us to a certain amount of accuracy for finding the fault, and in most cases we're going to see something very visual. But when you're developing your plan, put together your call list and notifications and maybe alternate services, etc. Okay. The troubleshooting flowchart, if we look at this is for a basic fiber optic communication system. I hope it's large enough so that you can read it. But from the top down, the first one is we have an alarm. We know that the fiber's in a problem and having a problem. At that point, it's a case of saying, do we hook up an OTDR right away, or do we want to measure power levels? In other words, the transmit level and the receive power level using any optical power meter. Only till we get past that stage do we normally involve the OTDR. However, as we're going to talk about later, there's several newer types of OTDR products out there that can be built into your system's management system and interface with it to provide more immediate information to the operator. But again, depending on the complexity of your system, then you'll need to decide what's the right approach for you. Now, as far as the field check, the verification of site location. So if the OTDR told us that the damage is at 12.6 kilometers from the central office, then we want to send somebody out in that segment to visually drive it and look for the site location. This also allows us to address some other issues such as safety and at what type of outage is it, do we have safe access to the site, and what type of equipment are we going to need to be able to perform this. And this may bring in different managers or supervisors that have different responsibilities. And so in this case, we've identified a few potential titles that you may be using. And, of course, we have to initiate the emergency restoration plan. So, when we look at the full system outage, safety is number one, in that we don't want, if there's high voltage lines down, until the power company cuts the power, we can't get access to it. And that, at the same time, we have to determine the work area and the environment on it. And where could we do the repair? And just because the cable's broke at one location, that doesn't mean that that's going to be our splice location. It may be better to move the splice location to somewhere that's more accessible, and that even though it may not be as quick. So we're going to deal with temporary splicing, and we're going to deal with permanent splicing. And it could be based on your different plans, but it could also be based on history, safety. We're going to talk about damage that may be away from the actual break point as well. So some of the bullets are items that you need to consider. The deployment of equipment and cable and hardware requirements. Can we start prepping the cable enclosures in advance and testing? However, one step that I've been talking about and we haven't got here is we're going to be using that OTDR to determine where the damage is, not just where the break is. We want to know both before the break point and after the break point if the damage extends any further back. And this could be different areas, for example, the landslide or the washout, where the cable's stressed far further back than just the break point itself. And that's where we want to cut out that whole section. Where if you're looking on the field, the construction, whoever's there, the construction manager or whatever, he may not see the optical damage. All he's seeing is the physical cable damage. And of course, if we're going to do a temporary restoration, and and most of your fibers are hot, then we're going to have to be rolling circuits, which means good communications with both ends of the cable span. And to move from a temporary restoration, also to plan for a permanent restoration as well. Okay, and again, different picture. This one happened to be a fire that took out a whole series of poles and different types of damages. But again, the steps are pretty much the same you're running through. But identifying the extent of the damage is very critical. And again, turning up the primary fibers as soon as we can. So finding the fault. One thing, most OTDRs are pretty common with single mode OTDRs are common to have a 1310 and 1550 nanometer module. We want you to use the 1550 nanometer because it's more sensitive to macro and micro bends. And we want to use the real-time functions to identify the fibers with Fresnel reflections. And now, for those that aren't familiar with the term Fresnel reflection, it's an abrupt spike. And anytime you have a connector, you'll get an abrupt spike. But if you have a break, you're not going to get an abrupt one because it depends on how the fiber broke. So if it's relatively flat, yes, we will. But if it's not flat and shattered, and on top of that, if you have index matching gel in your cable or it's underground and there's water, it's going to suppress those reflections. I'll put the OTDR in real time, and I'll just start with testing fiber 1, 2, 3, 4 until I get one that has a reflection. At that point, I can put the cursor there and I can zoom in and get extremely tight on where that break actually is. And then what I'll do then is I'll compare that one to all the other fibers, and now I know where the break is, how far back is the stress. And that's why we're going to use the 1550 nanometer or the 1625 nanometer, which we'll talk about a few slides up, and that specifically. So we're going to use the 2-point measurement because, remember, we're going to measure from the last known splice point to the break point, not from the CO. We're far more accurate to measure from a previous known point. We're going to expand and contract the vertical and horizontal resolution to give us the best image possible. So we're depending on the technician's skills to be able to understand how to use the OTDR properly in a restoration. And so let's move to the next slide here. And so here's an example where we're testing the plant with an OTDR. On the graphic, we're seeing different, splice points, which are standard. And then all of a sudden we see a roll-off that occurs. But we knew that splice 5 should have been there. So the fault's before splice 5. So what we're going to measure from is we're going to measure from splice 4 to the break. We're not going to measure from where the OTDR is located because we already know physically where that splice number 4 is located, and therefore we can use our sequential markings from that cable there to the OTDR to reconcile for the greatest accuracy possible. Also, the diagram below, if you look at where the break occurred and then the pre and post stresses, the pre-stress was 56 meters ahead of it, and the post-stress was 26 meters beyond. So we don't want to just cut that break out and resplice. We want to actually cut back that far and replace that section. Hopefully it's retrievable slack and we'll be able to recover that much. If not, we're going to have to splice in a section of cable, and in this case it would require 2 splice closures instead of 1. So you could have 2 crews working at the same time there. Okay, and so we're looking for the true physical location. The fiber roll-off is one of the signatures of an OTDR, and this is on the left diagram shows one where the fiber span's coming across, and then all of a sudden, we just get it where it rolls off down into the noise. Now the right diagram shows a minor Fresnel reflection. Okay, and this is where we want to use it as our base reference because we can put the cursor right at the knee of that reflection for the greatest accuracy. And now remember what I said about real time where we have the OTDR on. Once we get that setting on that, we can look at every fiber, and what we're looking for is instead of a nice uniform or linear trace coming to the Fresnel reflection, or where it should be. We're looking for any trace that is being stressed prior to the restoration itself. So in this case, I would zoom in on that point, but I would also enhance the vertical scale so I can see minute stresses far better. And remember that water and cable gel absorb optical energy, and they're much closer optically to glass than air is to glass, which is why we tend to see it absorb more. Okay, execute the emergency repairs. So again, you should have a plan, and so what you want to do is follow the plan. Whether it's a temporary or a permanent restoration, you may end up on a non-retrievable slack with 2 ends, so you're going to have 2 different pairs of technicians working, and so one thing we can do is start prepping the existing cable ends while we get materials being delivered on site. So this way, 2 of the 4 ends would be prepped already inside this splice closure. And then once we get the cable in place for the permanent restoration, then we can take that cable into the splice closure and perform your prep, and then therefore after that your splicing. And again, this takes time, and we're trying to repair as soon as possible. So the case is saying, is it more important to get the splicing performed, knowing that you will come back and you'll do final dressing, and that you can absorb additional losses? For example, if you have a 5 dB safety margin on that span, and you're trying to hit a 0.1 dB fusion splice or so, say it's not that important. Let's get this up and running, and whether you take a 1 dB splice, it's not going to affect the system performance. We're going to come back anyway, and we're going to do permanent splicing. So he says, well, it's a 0.3, and we're normally doing a 0.1. Who cares? Repair it. Get it up and running. If you're doing a temporary. If you're doing a permanent, then you want to, of course, get the best splice quality, but that's going to take more time. Okay, and then you'll always be testing with the OTDR to get your new measurements, but the optical loss testing would be end-to-end test, and that would depend again on whether it's temporary or permanent. And that permanent, you do new optical loss testing. Temporary, you normally just go with the OTDR. And so once we performed the permanent repair, then post a temporary restoration, then we want to make sure that we have new documentation that gives us the new values. And of course, if we're going to execute permanent repairs after the initial, we have to go through the same scenarios, making sure we have safety address, access to the splice points and the right materials and the scheduling. Post-recommendation, redocument everything that was, every fiber that was tested. And of course, you're going to deal with this with priorities. You say, we got to get these fibers up. Well, test them first. Get them up and running, get your measurements, and then go back to the lower priority fibers, possibly the proper sequential ones. Update all your as-built drawings. If you used emergency restoration kits or inventory, replenish those. And then have a meeting and review the restoration event. And this could be multi-departmental. What happened, what was preventable, what worked, what didn't work, how can we improve? So the report and the records, we should be addressing that report, the type of the outage, the weather, something not here, but it should be the weather as well. What was the cause of it? What was the weather of the event? What was the weather during the restoration? What was the geographic area affected by the outage itself? We want to address the effects that customers had, the time sequence, what we did, was everything in step in the best methods possible. Did we have any equipment problems? How effective did the team work together? Was there any shortcomings that need to be addressed? Is there any repairs that need to be taken care of? And then you're going to be updating your documentation. And again, we're as good as our documentation, and especially for future ones. Okay, so I want to go and talk about what some of the recent standards activities have been bringing up. And so emergency restoration itself is typically not a topic in a standard. However, maintenance is, and monitoring of networks. And the International Telecommunication Union's G Series, Transmission Systems and Media, Digital Systems and Network Standard, refers to the ITU's L Series, construction, installation, and protection of cables and other elements of outside plant standards. The first of these is G.39, Optical System Design and Engineering Consideration. And what it's done is it identifies the ultra-long wavelength band, which operates from 1625 nanometers to 1675 nanometers, as a recommendation for maintenance of fiber optic systems. Now, the next standard, the L.40, titled Optical Fiber Outside Plant Maintenance Support Monitoring and Testing System, also includes quite a bit of really helpful criteria. What can we do to prevent, and that what do we do post-installation or post-fault maintenance? How to use the OTDR and or the power meter, the different testing at different wavelengths, and can we do this without intruding into the fiber's operational system, which we'll show you a chart in a couple slides. Things that consider the signal quality level, for those that lease fibers or are providing fibers. Also, the alarm issues and supervisory systems themselves, and attenuation thresholds. Taking this one step further is the L.41 standard, which is more specific. This defines the maintenance wavelength systems for those that operate at 1310, 1550, and 1625 nanometers. So for those, the maintenance wavelengths are 1550, 1625, and 1650. So they're up one jump optically. And what this standard states is that in-service maintenance should not interfere with normal operation and expected performance of information channels, sometimes called optical supervisory channels. So there's 4 cases that are defined in this standard. So case 1 is the assumption that the system is operating at 1310 nanometers. If that's the case, then the next 3 windows are vacant and can be used for maintenance. In case 2, it's saying that the 1550 nanometer window is active, and we could use the 1310, 1625, or 1650. And again, on the case 3, now we're seeing a basic wide WDM system at 1310, 1550 nanometers operating, which leaves us two maintenance wavelengths, 1625 or 1650 nanometers. And the last case is that the system, say it's a DWDM system operating at 1550 nanometers in the C-band, but the 1625 nanometer window is being used as an optical supervisory channel for handshaking functions. This is not that uncommon, which means that we would need to be testing at 1650 nanometers. And so what does this mean to you? Now, number one, when you're looking at buying new OTDRs into the future, at a minimum, you would like to have a 1625 nanometer laser in that OTDR, preferred a 1650, or if you know, if you're non-DWDM, where we have the handshaking occurring at 1625 nanometers, then in that case, you would want to have the 1650. So you're going to have to determine on your system and that whether to buy a 1625 or 1650 laser, and the OTDR manufacturers are glad to supply either one. But this chart is the basic for that, why we want to be using those longer bands which have been defined for future maintenance applications. So why don't we talk a little bit about next generation OTDRs and that. Well, why wait? Because they're already here. They've been around for ages, especially the rack-mounted ones which incorporate an optical switch, and that they interface with the equipment subsystems and software. They operate out of band, which 1650 is out of band from an operational wavelength, and a lot of WDM options. They can operate 24/7, monitoring or on demand, and the case of the optical switch is one that if you're running from a hub site and you got multiple cables, then we could have an optical switch that switches between the different cables, and then by using the WDM function where we're at 1650 nanometers where we won't interfere with the transmission systems, this will allow us to look for stresses and faults and that while not interfering with the operation of the system itself and that. And so most of the major OTDR manufacturers provide this type of equipment, and it's worth investigating. It does have to be incorporated in with your alarm structure and that. And because the 1625 and 1650 nanometers are so sensitive to macro and micro bands, they will be detecting stresses that your 1550 nanometers OTDR may not have when you did your initial testing. It can also be, though, that you're going to find faults and splice closures and that are going to look very lossy in the longer wavelengths, but still operate well in the shorter ones. And this is just due to the sensitivity of these wavelengths, which is one of the reasons why it was selected for use. Another type of next generation is putting coarse wavelength division multiplexing optics into OTDRs. So in the different bands these are 20 nanometer bands or channels that have been assigned for CWDM by the G.694 channel assignments standard. That you can now, if you were saying using a ring architecture and certain wavelengths were being used by different users, that you could have an OTDR that would be able to just test that one wavelength. These also give you the ability, if you bought the channel that includes 1383 nanometer, that you could look for high losses and know whether you have pre-G.652D low water peak fibers installed. And that otherwise your conventional OTDR will not be able to test in the E-band at 1383, but a CWDM would be able to. And the attenuation at 1383 is about 2 dB per kilometer versus our standard 0.4 dB per kilometer at 1310 nanometers. And that. So anyway, CWDM is a good technology. It allows us to add capacity to a fiber network easily. Just have to watch out for the E-band because of the water peak in that band, and that CWDM OTDR can test that band. So let's look at another type of OTDR, and these are using the SFP module format. And we'll see a picture of this in the lower right side. And also a schematic courtesy of Optical Zonu. And in this case, they have several options, actually. One is if it's a bidirectional transmission, and the other is if it's a traditional two-fiber, one transmit, one receive system. And if you look at the schematic, you can see that it's actually not only an OTDR, but it's actually functioning as part of the network itself as well. And the advantage of this module and this approach is it identifies immediately within minutes that there's a fault or a stress. And it can give you a relatively good accuracy because it's based on the index of refraction that whoever programs the system puts in, which means we're only as good as that index of refraction number. But if we can get within X amount of meters from a fault, we know that it's broken, and you can do a truck roll to say, we got to find this, it's out here between splice points 2 and 3 or poles or whatever, then you can start the investigation far earlier than it would to take the time to have somebody come in with an OTDR, hook up the OTDR and look for it. We're talking saving at least an hour by this and that. And so if immediate response is important to you, this is a good solution. These run in the price range of hundreds of dollars, not the high end, but the lower end. You'd have to talk to the manufacturer, but they have a lot of different models with a lot of different dynamic ranges based on the optics that they would be putting in. So one more slide on this is, again, different classes for different range, different dynamic ranges for them. Operates as a system transceiver until failure or power loss occurs, which means that when you're first bringing up the system that it has to incorporate the data into the program or, your benchmarks, shall we say. Okay, so in summary, I wanted to say history repeats itself in fiber optic outages. Remember that whether it's twisted pair coax, if you have an event of landslides or typhoons or, tree branches, it doesn't matter what the media is. It's going to occur. So you base your plan on your history and that, or on a fear of something that you say may happen. In that case, we want to try to construction engineer ourselves around it prior. The emergency restoration plan should be part of the outside plant design, as well as the additional losses incurred in this should be incorporated in the safety margin in the transmission system itself. There are new types of OTDRs available to address new technologies. We're seeing much smaller component costs, therefore we can have an SFP OTDR where we couldn't have this 10 years ago. And that we're seeing standards that are identifying maintenance wavelength in the ultra-long band between 1625 and 1675 nanometers, and they should be taken as part of your plan itself. So we know that planning is critical. Documentation is essential. That you have to have the right equipment and staff skills and training, and we never diminish the importance and the critical nature of safety. And as the Light Brigade, one of our goals is to develop training courses and materials that go into the different types of needs. And as you noticed in this presentation, I didn't really go into step by step on the 20 or 30 different types of restorations for aerial and underground, retrievable, non-retrievable. Those are part of our courses, and it just takes so much time to be able to incorporate those into an hour-long webinar. So at this point, let's start looking at some of the questions here. Little slide on what we have an upcoming emergency restoration course in Denver, but we take these courses on site worldwide and teach, and sometimes co-developing a program for you as well. And we also have a whole series of DVDs, and the testing and troubleshooting DVDs, a real good one for $99 or something. So what I need to do now is answer some of these questions. So we'll start on what are your thoughts on emergency restoration kits? And to me, it's one that says you really should be building your own. It's very hard to find one kitted that's going to meet your requirements. Let's see, can we go up to, okay, what's the, let's see. I'm trying to read, and as I said, eye surgery about a month ago, and some things look a little fuzzy. What's the difference between cable length and fiber length? Okay, the fiber is always longer than the cable, and it's due to the way that the cable is manufactured. Because the cable expands and contracts, there has to be more fiber length into a given amount of cable. And so the cable length will always be shorter than the fiber length, which is why we want to compensate and adjust the index of refraction so they match up. So if you are adjusting your index of refraction, the number will actually increase from 1.471 to 1.4, say 91 or so. But you'll figure that out once you know the physical length of the cable, and then you reconcile that one. Okay. I'm trying to, the question about a standard, okay, due to the fact that it is a European technical specification on the topic of repair of damaged optical fiber cable, in my mind, this TS should become an IEC standard. Maybe we can communicate offline on your question, because it seems to be opinion and all this, and I'd love to hear from it and know more about it, but I'm not sure I can address this as a question. So we'll go to the next one, and we'll talk later. Why teach emergency restoration in metric? Well, because most of the world's in metric, but if we want to be teaching it in footage, we can definitely do it. But it's up to each provider whether they're going to do their documentation or metric or footage. It's not for me to say. But we have people from around the world on this webinar, and so therefore we have to address it from both the national, North American, as well as an international perspective, which is why we're covering both metric as well. Whatever technique you're going to use, which is best for you, is fine. Just stay consistent on it. That's that. Okay. Okay. Can an SFP test through a splitter accurately? Good question, but I wouldn't think that it would be a problem, because testing through a splitter is based more on the dynamic range of the instrument versus the passive component. Okay. And how accurate do you find the built-in rack mount OTDRs for field equipment? And is there also anything that tests past optical splitters and GPON architectures? Yes. What you're looking for is you really want to be seeing about a 43 to 50 dB dynamic range if you're talking about a 1x32 splitter, whether it's centralized or distributed. That's number one. You have to have the dynamic range. Number two, you have to have the averaging for it. But if you want, contact me, and my email address is larry@lightbrigade.com. We're about closing up here anyway, so why don't we put on our just the last closing slide here for a sec. So my email address is larry@lightbrigade.com. I may not have answered everybody's question, but we're up against our time limit here. Do feel free to communicate with me, and I will email you directly back, and we'll also be sending out an email in the next day or so as a follow-up as well. I really want to thank everybody for attending. On behalf of the Light Brigade, we'd also like to thank Lightwave and the Pinwell Corporation. And as I mentioned previously, the presentation will be archived within 24 hours and can be accessed through the Lightwave homepage. Again, remember that a reminder email for the archive will be sent to all registrants. And if you want a copy of the presentation, you can also email us directly in that port. So we thank you for joining us today and look forward to providing you with a future forecast. And do we have a last slide? We do have another webinar we're doing in September, and it's called Tier 1 and Tier 2 Testing Best Practices Overview, so we hope you will attend it as well. So thank you very much. I look forward to further communications with you.